And we're back. Let's sort it out with Mr. Swartout. Here we have a work problem, tension applied at an angle, and we're going to include friction here. So this is about as advanced as you can get for this type of problem. So let's get started. We want work done by tension, work lost to friction, and then final velocity. So start by breaking down that tension force into components. Then we can realize that the work done by tension would be just the x component. So using that expression for work, FD cosine theta. Then we want to know the work lost to friction. So here we're going to need the friction force, and then we multiply it by the same distance that the block travels. So the friction force, mu times the normal force. However, we are pulling up with a rope, and that's going to lessen the normal force. So you can see a previous video for how we got this, but the normal force in this case would be the weight of the block minus the y component of the tension. So that would be the normal force here. Then, because we're pulling up, the normal force is less than it normally is. That means that the friction force is going to change because friction depends on mu and the normal force. So that's what we have right here. So then the work done by friction would be mu times the friction force, or sorry, mu times the normal force times the distance. So all that would be the work done by friction. All this refers to the friction force, and then that's the distance that it traveled. Okay, then we can do work energy theorem. In this case, we calculated both of these, so it would be simple to do net work where we take the work done by tension minus the work done by friction. Those are in opposite directions. Set that equal to the final kinetic energy, and then from there go ahead and rearrange for the final speed. So this is an expression that will solve the last piece for the final velocity. And there you go.